Hello and welcome back to Humans versus AI video 11 this time. And today we're going to be extending our PPO module, which is the wrapper around our game, so that we can basically train a machine learning agent using the game. The game is going to form our playground, which allows our machine learning agent to explore options and get rewarded and penalized based on those options. But to do so, the whole game needs to be wrapped in something that allows us to interface with the game functions or methods, and can step through using those methods to basically simulate the game being played. So that's what we're going to do. In the last video, we looked at state, and actually that's where we're going to pick up today. Reminder first then that I have a Patreon account, and a big thank you to all those who already support me. If you would like to become a patron of mine, you may do so at the link. And as a thank you, you will receive access to the code that you see in the videos. There's basically a Google Drive folder where you can see every episode, so you can go along with the video series. Anyway, enough of that. Let's go over to my IDE and progress. Okay, so I'm just going to start where we left off in the last video, because there's something I didn't do, which was I didn't really show the state. And this time I'm going to show the state. So in the last video, we created this, which is, if you recall, within the onUpdate method, which happens with every game loop, every frame. When we loop through the players and check that we're not in training mode, and we check that this isn't a human, we go through to the new piece we developed in the last video, which is the machine learning piece, which is where we're going to allow the machine to make decisions and actually play the game. In this case, then, we're extracting the state we're calling state. It's a NumPy array because that's what stable baselines, which you're going to use, requires as an input into the machine learning model. So that's why it's wrapped in an NP array. But the important part really is these two things, these two methods I'm going to highlight. You get game state and flatten game state, which we wrote in the last video. I'm laboring this here because the output from this I haven't really shown and explained. I've just said, here's what it looks like, this is why we need it, we normalize, we order it in a certain way for good reasons. We went through all of that, but really I never showed it in the end, and I realized that. So I'm just quickly going to show you what it looks like. So what I've done is I've made it so that the game has just one player. I've made the game player speed really, really slow. So it gives us lots of time to have a look at what the state is when the game first initializes. And then we can talk about what the game state looks like. So I'll press play. So a bit of a Blue Peter thing here. I've set it up ahead of time. Okay, you can see the player is very slowly moving to the right. Because if you remember in the last video, as a placeholder, I passed an action which was a value of 3, which equates to move right. The target position had been set to one grid cell to the right. Anyway, whilst that player moves, let's have a look at the state. So we can see we've got 4 energy points in this particular scenario, and this beneath in the console, which hopefully you can see, is the state. I can't highlight with my mouse because I lose the window. But the player's location at the point that state has been printed is just here, and it's looking at the relative position of the energy to the player. That's what the first few data points are in this array. It's x, y, x, y, x, y, x, y for 4 data points. That's the first 4 data points of the state array. And then the last 4, these 4, are the relative distance. So they're just scalars, they're just relative distance. So if we look at the first data point then, x, y, it's 0 in the x direction and minus 0.1 in the y. Bearing in mind this is normalized, well, you can see that must be this data point because the player was here. And then the next one is minus 0.3 in the x and 0.2 in the y, which must be this one. So you can see we've got the x and y coordinates for each relative position of the x and y coordinates for each energy. That's the state array. And then the last 4 points are the relative distance. So 0.1 for this one, 0.3 for this one, 0.4 for this one, and 0.447 for this one. So that's basically what the machine sees. And when this player does snap to grid into its new cell, another state will be printed, which will be slightly different. There we go. And you can see all of the numbers are slightly different because the player is in a new cell, and therefore its observation, and therefore the state is different. And so the machine will get this information and be able to make a decision based on it because things have changed. So there we go. Okay, so I don't forget, I'll delete that. Right, today we're focusing on the PPO method, which is imported into main up here. There it is. So let's go over to that. In the last video, we did set up the basics. We had these imports already. We had the structure of the class in place. We didn't have the environment, gym environment, that we've got here as a parent class we were importing, we're inheriting from, sorry. So there are a few changes. So let's walk through those. Before I do, just a reminder, PPO module, I've named it PPO, there's nothing special about that name, is the wrapper. It's the wrapper, and it's purely for training. When the model is running, we don't need this at all. PPO is just for training. So first thing then, we're going to install some dependencies which are very important. The first one is stable baselines 3, and we're importing their implementation of proximal policy optimization, which is a reinforcement learning, I should say, model or approach. It's really an approach, to be honest, an algorithm. So that's what we're importing so that we can make use of it. It'll cut a huge corner off our development time by being able to do it. Basically, they've got a well understood and implemented version of PPO that we can lean on. It's not a trained model, but it's an architecture that saves us having to code it in, and it's efficient as well. There's two imports actually. The other one is going to be for callbacks. So I won't get into this now because we'll get to it when we get there, but we will be wanting to use callbacks so that we can see what's going on as the model trains. That's important to visualize what's happening. So we'll get to that. It's not absolutely required, you can do without it, but you will struggle, as you'll find, if we can't visualize what the machine is doing. So that's what the second one is for. So pausing on stable baselines then, stable baselines 3 in this case, we need to import it. So you know how to do this. I'm not going to go into the details, but in my implementation, I've got pipenv for my package management tool. I've gone already into my video environment, and if I wanted to install it, I would type in pipenv install, which is equivalent to pip install, and then stable baselines 3. That would be installing stable baselines 3. And if I were to look inside my pip file now, I'll find it, and also gymnasium. So you'll see that I've got additional installs now in my environment. I've got arcade, of course, pillow, numpy, stable baselines 3, and gymnasium. Gymnasium we're going to talk about now then. Same thing to install it. Gymnasium is the thing that makes this PPO module a wrapper around our game. Gymnasium is all about creating spaces for us to interface with the thing we want to explore, the environment. So Gymnasium actually has built-in environments for certain fun projects you can use if you look into it. I'm using it as a means by which we can access certain methods that allow us to interface with my game. And it gives us access to methods that I'll talk about in a minute, and it'll all make sense when I do. Okay, so we'll move on. So they're the imports, and that's what you need to do. Don't forget to install Gymnasium. So we've seen this before, PPO is our class, but we're now inheriting from Gymnasium environment.env, so make sure that we put that in. It's important because we're going to be using that. The next thing is, I don't know if I mentioned this in the last video, but we're initializing a variable here called training iteration, which is to count how many training loops there have been. And as I mentioned in the comment here, that's a very useful thing to track for many reasons, but the main one is rendering. If we want to render the game, we want to do so at every so many iterations, and tracking the training iteration is very useful, so that will increment as we go. And then we have the constructor, basically. And I've got a few bits here. So the first thing is, and we talked about this in the last episode, it's importing GameApp as a parameter to the constructor. So GameApp is an instance of the game. So this is how it acts as an app, as a wrapper. We're going to need access to the game's methods in order to run the game step by step manually. So that's why we need access to the game. So we're going to pass that through when we initialize the constructor of PPO. We'll pass through an instance of the game environment. That will then allow us to use things like, for example, it'll allow us to use things like setup and on draw if we want to render the game, on update, which of course is critical because that's where the state is. In fact, on update is really critical because that's where we're going to apply the action that the machine suggests. Okay, so that's why we need to get GameApp. And then we also have a couple of additional variables that we're going to be storing within the PPO class. So these are kind of member variables. You've got episode lengths, which is an array, and step in episode. Right, so this is where I'm going to pause and just explain a little bit about PPO, or in fact, reinforcement learning in general in this case. So the way it works is that the training is broken down into episodes, which are then kind of all comprise of a rollout. That was terribly explained. I'll work backwards actually. A rollout contains lots of episodes, and an episode contains lots of steps. In our world, for this game, a step is a frame in the game, or, as you'll see when we get there, I don't wish to use a frame, but we could have done. I wish to use an opportunity for a decision to be made, and that opportunity is when the game player is not moving, so when in transit is false. So whenever that happens for a particular player, that is a step, because that's when a decision can be made. There are lots of steps in an episode because an episode terminates when we say it terminates. We're in control of that, and we're going to say that an episode terminates when the game is over, when the player has collected all of the energy in this case. So that's why we've got steps in episode. We want to count how many steps have elapsed throughout an episode until the game is completed. There's a really good reason for this. It's useful for many things, and we'll see why later on. I won't go into it now, but it's very useful to take a record of how long each episode is taken, because in this game in particular, the episode duration is a really good metric for how well the model is performing. The shorter the episode, the quicker the player has won, and therefore the more efficient the player's moves have been in getting all of the energy. So we're just going to record the number of steps per episode, so the number of decisions that have been made until the game has been complete, till you get game over. And the episode length is just an array saving this number at the end of each episode, okay? Right, hopefully with that makes sense. I know we're not using it yet, so it's a little bit abstract, but they are important. So that's the constructor. Moving on then to a few methods. I'll just show you what they are. We've got reset, we've got step, and we've got calculate reward. Two of those three are provided to us by Jim. We've got reset here is the first one, and we've got step. They're both methods that are going to help us work with the game and run the game. So for example, reset is run at the start, but it's also run, hence the name, every time an episode is complete to start the game again, which makes sense. We want to compartmentalize the game. We want to compartmentalize what the machine is learning. It needs to have a horizon, so it doesn't want to go too far in when you're trying to train it. So for me, I'm restricting the training to the end of, you might call it a level. It's where the player has collected all of the energy. That's when reset will be fired. Now you might be wondering, how does it get fired? We'll get to that, but it will do. It'll get fired when the game comes to its conclusion and it says game over. But then we want it to do it again and again and again so the machine can learn. But reset needs to happen because we need to tell the wrapper, well, what do you do when the game starts again? It has no idea even what the game is. So this is where we tap into the methods that come with main that we've grabbed from game app. If you recall, we're passing game app through into the constructor, so we now have access to the methods that we've got in main, because when we initialize a new instance of PPO, we're going to pass a game environment through that's already been established, and therefore we get access to the methods. And therefore we get access to setup. Now if you remember, setup's in here, so if we go to main and go up to setup, there it is. Setup is basically what performs the sanity checks, what creates the grid that's rasterized for performance reasons for the background grid. It sets up the players and it sets up the energy. So unsurprisingly, it sets up the game. So we've just done that from outside of the game. We've just used this wrapper to reset the game. Now, I'll actually pause a minute because I was going to mention this at the start. Each of these methods that are provided by Gymnasium have to return certain things. It requires those things to be returned. In the case of reset, we must return an observation and an info. Now, info is very useful for passing additional telemetry through, but at the moment we don't need to use it, so I won't confuse the issue with that. So info is blank. It has to be blank, so that's what's going on there. Observation, however, is our state. It's called observation because the game state is the observation in reinforcement learning. So it's been named observation here, but you will find familiar that line. That is the same line that we've got in main when we're getting the game state in onUpdate. It's the numpy array with flatten game state, flattening what get game state provides. Okay, Another interesting fun fact is, if you remember, getGameState takes as an argument a player, but we can get the player from the game because we've got access to game. Now, the game can have multiple players, but why? I'm just taking the first player because I only ever want to train on player 1. So player 0 is the one that I'm putting in and getting the game state for. So when the game resets, that gives me an observation. Okay? The last thing I'm going to mention here is step in episode necessarily has to be reset. We talked about the importance of counting the steps in an episode. Well, when reset runs, the episode is concluded. So we need to reset that number. And then we return the observation and the information and info, which is empty. So that's reset. The other one is, actually, before I go to step, I'll just go down to calculate reward. Calculate reward is not from Jim. That's my method. But it is required that we have a reward value coming back from step. In fact, if I go to the bottom of step and have a look at what's returned from it, like I just said about reset, there are certain things that have to come back. One of them is reward. So necessarily we have to calculate a reward for a given action that the machine has taken. That's part of what step does. I'll talk about step in a second. But if we're talking about calculate reward then, simulation equals false, you can ignore that for now. That's actually, in a sense, an accident. This is something that will be put in a later video, but I'll leave it in for now. All I'm doing here is creating a placeholder. The reward will be a value as big as we like and as small as we like, but it needs to be relatively sensible, which we'll talk about when we come to calculating rewards. It's the thing that we say to the machine, this was good or this was bad. Low values are bad, high values are good. And at the moment I just have a reward of 1 as a placeholder and I return it. But you'll see we're using calculate reward up here because we need to return reward from the step method. But let's get into the step method now. But I just wanted to show you what calculate reward was. It's a method that I created, and at the moment it just returns a value of 1. So the step method essentially takes an action, which you can see is one of the parameters of the method. The action is given to us from our point of view here, from the model. It's basically the model's output. And then essentially what step wants back from us by the end of the logic that we've written here is what is returned, which is mainly the state, the bits that matter are the first 3. The state at that moment, the reward that we've given it, and the status whether or not the episode has been terminated. This is how Gymnasium knows if we've terminated the game, and therefore the PPO model. So great. So let's now talk about the step function and how we're going from action through to basically state and reward and terminated. Firstly, we assign the player to player 0 like we did in the reset method. Then we update the game state. Now, delta time, I haven't put it in yet, but this is a custom value. We can decide what that is. Basically, the game will run, if you're running the game with arcade, at about 60 frames per second. This basically is saying how fast do we want to run the game? What is the increment that we want to move the game logic along by? So if we go back to main, you'll notice that onUpdate does take delta time as an attribute. And we calculate the FPS here, and we update the player positions using delta time. Because if you remember, we don't want movement to be based on frame rate. We want movement to be based on real time. Now, delta time comes to us from onUpdate. And if you remember, onUpdate is a method that comes from arcade. So arcade gives us the time between frames, and therefore we use it to calculate the FPS, but also to update the player's position using delta time so that it is independent on the frame rate. Okay, so we now know that arcade gives us a delta time. Well, we're not using arcade with PPO. We're wrapping the methods of the game, but we're not using arcade. We don't have delta time being provided for us. Furthermore, we wouldn't want to use 60 frames per second. It's excessive. So we want to pick an increment that makes more sense for training. We only need to do it occasionally, move the game forward, occasionally. So I haven't included it above. Basically, I forgot. But self.delta time is going to be, I could put it up here for now, maybe to remind myself in the next video. It belongs up here. And let's say it's 0.1 seconds for now. This will be a constant eventually. Hopefully that's clear. This bit's interesting. So step can't go beyond this line until the player is no longer in transit. So it'll loop an update, running game update, until player.inTransit is false, i.e. the player has reached a grid cell. So that's interesting. And I wrote this because I didn't want the game to make a decision at every delta time, because the game would try to make a decision, no change could be made, because in our game, this game, the player can't change direction whilst it's in transit. So the machine would really struggle to learn. It's making decisions, but nothing's coming out of it. So we only allow the machine to make a decision, i.e. we only step this forwards when the player's no longer moving. If you're building your own one of these, make sure you take into account that you should only be training the model when it can make a decision that makes a difference. And that's basically what this code does. The next thing is we actually set the target position. So let's take a minute and go back to main, just pause on there, and let's just go back and look at this. So if you remember, in onUpdate, we had a new bit of logic in the last video, which said, don't run any of this code if you're training. And I said I'd explain why it was. Well, now I'm going to explain why that's the case. So if we're not training, we want to play the game. So if the player is playing, we need to handle the keyboard to set the target position. If it's a machine, we need to get the machine learning, which will go here, to make the decision and then set player's target position, which at the moment we're doing with this method, and at the moment we're faking it with the number 3, if you recall, which is an action. Okay, great, but we're saying we're not going to run this if we're not in train mode, which is important because of what I've just said about not going with every increment. We want to be able to loop through until in transit is false. And therefore we don't want to be making movement decisions. We don't want to be running all of this with every increment. We want to just do it when we want to. So what I'm saying is this is purely for playing the game. If train is false, this will run. If train is true, it won't. And therefore we need to be able to still move the player. And that's what's being done here. In PPO, we're tapping into the game's ML set target position, which is, of course, what we do run in this loop here. To set the target position based on the action from the step, which is the other reason we want to take control of this, because we need to set the direction, the action for the player based on the action that we get back from the model during training. Now, if we did it in here, we'll be getting the state back and we'd be running it on a different model. And the reason is because in here, what will happen that you can't see yet, we'll be using a model that's already trained. We'll be loading it in to play the game with that trained model. But at the moment, during the PPO training process, we don't have a trained model. So the action can't come from a trained model, which it would do here, based on the state it's passed. We can't, so instead, we need to provide it with the action that the model suggested. So that's why, again, we take control over this and take this outside of the game, and hence the on-train logic. I hope that's sensible, makes sense to you. So, okay, so we've looped the step. Sorry, the step hasn't moved until we've looped through the game state until the player is no longer in transit. So let's just, actually, I'm just going to go back, hopefully, just if that wasn't clear, one thing I will say is onUpdate does more than just change the target position of the player. Of course, it also updates the player's actual position. So this is outside of the if not train logic. So this will run no matter what. And this is what's actually moving the player. We can't set the target position here because we're in train mode. We're going to set that in PPO. But the actual update position logic, which actually moves the player at the right amount based on delta time, that is still running. Therefore, as we loop indefinitely here, the game is moving forwards because the player is moving until they're no longer in transit. When they're no longer in transit, the whole method continues. We set the new target position, so of course it's going to be in transit again in a minute, but at the moment it isn't. We get the state based on where it is now, which you've seen before, tapping into the game's flattened game state and get game state methods. And then we calculate reward, which is the method we looked at a few minutes ago, which I created, which is currently a placeholder. But eventually calculate reward will be sensible and very important. Reward shaping is the heart of everything in reinforcement learning. This is going to be where we define what we want it to do. This is the fun bit, because it's like, well, it's up to us what we make the game do. So I like this part, and you'll like this part, I know it. And then terminated. Is the game over? Well, we're tracing that already in main, and we call it the game over flag. It's a Boolean. So we tap into game and say, is it true or false? If it's false, we don't do anything. If it's true, we're going to append episode lengths to the array that I mentioned above. Sorry, we're going to append, step in episode to episode lengths. If you remember, episode length is all the way up here. We're recording basically how long each episode is. So that's just a metric that we want to keep track of. And you'll notice here is where we're incrementing the episode step. Finally, I'll mention that info is required, but we're not currently using it, like we're not currently using it in reset. So the returned information from step is the state that we've calculated up here from the game. It's the observation. The reward, which is currently a placeholder, but will be very important soon. And then whether or not the game is over. If the game is over, this will be true, and step will know it, as will the model. Don't worry about this. This is truncated. It's another argument we have to pass. For now, it can just be false. So that's it. That's the end of this video. There's a lot there, but the principle is we're using this PPO wrapper to play the game without running arcade. We're using the methods to play the game. We've got reset, which resets the game at the end of an episode when we need to start it again. We're playing with player 1 only. We're updating the game state, which moves players around, but we won't continue with the machine learning training, i.e. what action has come out of, what happens from the action. We're not going to continue to see what happens from the action until the player's position is stopped. So this is what pauses it. We then set the position based on the action. We get the state. We calculate the reward for what the action was, and we determine if game over has happened. We record a few metrics for future use, and that's it. So calculate reward, step, and reset are the new bits in PPO. And that's it. There won't be anything to show in this video if I press play, apart from the setup I had before with the very slowly moving player, but we have established some important methods that are going to allow us to train the model. So in the next video, we're going to continue with this, getting closer and closer to being actually able to train the model by playing the game using the methods that we're tapping into. Thank you for your time. There's a lot there. If you're a patron of mine, please have a look at the code, have a run it, it'll run, and see what you think. Hopefully I'll see you in the next video.